And we're back with lesson 7.3 part 2. Remember, lesson 7.3 is looking at the sampling distribution of sample means. The previous video looked at case number 1. And that case was what happens if you take a sampling distribution of sample means of x bar from a normal population. And we analyzed the shape, the center, the spread, and we looked at characteristics of that. And that's where the first video, that's what it covered, and that's where we ended. Now we're looking at case number 2. And in case number 2, we're looking at what happens if you grab a sampling distribution of x bars from a population that is not normal. Now that could be completely right skewed, completely left skewed. It could be all wibbly wobbly shape. We have no idea. And one thing to know though is as your sample size increases, the shape of the sampling distribution of sample means is going to change. And that's really interesting. And I know you have the notes and you can read all the hidden black stuff there, but hey, this is where I'm going to have my fun. But I want to talk about one thing before we go into this is we did mention something way back in the beginning of the first video. And I just copied it right here as it said, hey, note, these facts about the mean and standard deviation of x bar are true no matter what the shape of the population distribution. And that's interesting because that's where case number 2 comes into play. We don't know if it's normal or not. So what's going to happen to the sampling distribution of your sample means? Well, there's this nice applet, and if I look at this applet, I can figure out what's going to happen. And if we take a look at this, here's what we have. This first we have here is the sample. So this first graph here is going to represent the sample. It's going to collect the sample, and it's going to go right down below to the next one, which is the distribution of mean. So it's going to calculate the sample mean. So just watch this. Now notice, you can't see the shape of the population. I have that hidden from you. So I'm going to collect, and it's going to collect 25 from there. It's going to collect a sample size of 25 from the population, and it's going to calculate the mean of that and plot it. So let's do that again. It's going to grab a sample of 25. So it's grabbing the sample of 25 from an unknown shape, and it's going to plot the sample mean in blue below. Now I don't want to animate that many times. Let's just click the 5 button and let's do it 5 more times. And it's not going to animate it, it's just going to plot the blue points down there. And so you have no idea what the population shape is. So if I do it 5 more times, what's going to happen? It's going to continue. And so we see this. Now, what if I do this many times? Now, let's just say 10,000. What if I do this 10,000 more times? And so if I do this 10,000 more times, look at what happens to the shape of the sampling distribution of means. You have no idea what the population distribution shape is. But if I do it 100,000 more times, we've done it many times. So I did 100,000 more times. And you look at it, that's the shape of the distribution of sample means of x bars. And if I click the fit normal button, and you look at it, that is approximately normal. You have no idea what the population shape is. No clue. But if I collect enough sample means, many times, plot the sampling distribution, the shape of the sampling distribution of x bars will become approximately normal. Now let's show the surprise. Here is the population to prove it to you. That is what I would call a wibbly wobbly distribution. Who knows? But it is not right skewed, it's not left skewed. It is all weird shaped. But notice, even though it looks like that, if I take the distribution of sample means, it's approximately normal. As long as I do it many times, and my sample size meets a certain requirement. And that's where kind of the one thing I don't like about this applet is it says n equals 25 down there, but that's not the magical number. So let's remove the black now. The magical number, the number that you want to figure out when it comes to your sample size, is that n has to be greater than or equal to 30, not 25. 30. So here's what we just showed. We showed that as long as you have a large enough sample being taken, greater than or equal to 30, from a population distribution, it doesn't matter what the shape is. The shape of the sampling distribution of sample means will become approximately normal. That's case number 2. So when you read the prompt, you have to ask yourself, does it tell me the shape? Yes or no? If it tells me the shape is normal, I'm in case number 1, my sampling distribution is normal. If it doesn't tell me anything about the shape, or if it tells me the shape is right skewed or left skewed, then I have to look at case number 2. Am I taking a large enough sample size to apply the central limit theorem, which says that if your sample size n is large, greater than or equal to 30, the sampling distribution of the sample means x bar is approximately normal. So here is the applet website. You can feel free to play around with it. And so I'll show you one more. And so I hid that one from you. I'm not going to hide this one from you. This is what's on your notes, give or take the shape. I just kind of clicked it. And the same idea. It is not right skewed. It's not left skewed. It is not normal. It is not uniform. But if I do this many, many, many times, and I'm going to do again, I can only go up to 25. And if I collect a sample many, 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 many times, so it's gathering the sample of 25, and it's calculating the mean, and it's plotting it down below, and that I'm going to repeat 100,000 times. So this was done 100,001 times, many, many, many times, and notice you get approximately normal as a shape. And you can play around with this, and it's really easy. You just use your mouse, and you can change the shape to anything that you want. And if I clear the lower 3 and I hit 100,000, it's going to do it and show you, look at that, it's approximately normal no matter what the shape. So it's a really cool applet to play around with if you're bored, and you can look at it. Now let's see. So that's what this kind of goes through. So these pages go through what I showed you on this website. And so this shape, who knows? But as I increase, and so what happened is on these slides, I did a sample size of 2. And I created a sampling distribution of x bars. And notice that really didn't do too much. So we went from this picture up here, this original, to the first blue right here. And it didn't do too much to that shape. It didn't make it approximately normal. But I went to 5 for the next one. And notice you start to see the information start to gather more and more and more around the center part of it. So it's not perfect at 5, and we never would accept 5, but you start to see the shape begin to change. And then we go to 10, and then we go to 25, and notice it starts to look better and better and better. And by the time we get to 25, and if we got to 30, we would notice that things start to become approximately normal, which is that bottom one shown here at n equals 25. And that's what's really interesting. So your sample size needs to be large enough. And that's what these pictures on your notes are trying to show you. N equals 2 to n equals 5 to n equals 10. You should start to see the variability start to decrease. And notice the spread. It becomes tighter and tighter and tighter. Less variability even in the distribution of sample means as you increase your sample size. It all starts to gather around the center, we start to notice as well. So that's kind of the main idea behind those pictures on your notes. So what have we learned about the central limit theorem? So here's what we know. The central limit theorem, the distribution of your sample means, x bar, from a strongly non-normal population becomes more normal as the sample size increases. And you can see these pink graphs here. And so you have a distribution, n equals 1, to n equals 2, to n equals 10, to n equals 25, and you start to see the sampling distribution become more and more normal. And that's what that applet really shows you. So case number 1, remember those are the 2 cases. Case number 1 says, hey, if your population is normal, the distribution of sample means is going to be normal as well, no matter how small the sample size is. However, case 2 says, If the distribution of your population is non-normal or unknown, you have to apply the central limit theorem if your sample size is large enough to approximate normality, and that large enough is greater than or equal to 30. So, in other words, read the prompt. Check random shape center spread in the prompt. If your prompt says the shape of the population is normal, great, you're in case number 1. If it says nothing about the shape of the population, doesn't say anything at all, or if it says it's right skewed or left skewed, or it says it's non-normal, then you're in case 2 where you need to look at the sample size and make sure it is large enough for the central limit theorem. So why sampling distributions? Well, sample mean principles. Averages are less variable than individual observations. And just think about that for a minute. You have a population, and if you grab one person, an individual observation from that population, you grab one person, it's going to have a large variability. Because you grab one person, and let's say somebody else grabs another person. I mean, you're just grabbing one person from an entire population, and you're looking at that. Now, that has a large variability. But if I grab a sample of, I don't know, 30, and I calculate the average of that, then I grab another sample of 30 and calculate the average of that, the averages are going to be less variable than individual observations. And also, averages are more normal than individual observations. And again, think back to the applet. The averages became more normal as I took more and more and more and more samples. Created a sampling distribution. So, let's try this out. So let's take a look at this. In this prompt, we are going to be given the same information when it comes to your mean of 3,250 grams, the same information with your standard deviation being 550 grams. What's going to change is some of the information that's provided to us, what we're calculating the probability of, our sample size. But we're still going to read the entire thing because there's little clues inside there. So the birth weights of babies at a certain hospital are known to have a mean of 3,250 grams and a standard deviation of 550 grams. What is the probability that a baby, and realize that right there, a baby, that means I have a sample size of 1. A baby, 1. What is the probability that it will weigh less than 3,000 grams? Now, we're not being asked to calculate this. We're just being asked to practice reading the prompt. What's the shape, what's the center, what's the spread, and can I apply the central limit theorem? Well, remember, the mean of your sample means is an unbiased estimator of your population mean. And so what's really nice about that is I can say that 3,250 grams is going to be the mean of the sample means. The spread, and I'm going to write this down, we're not going to check right out all the information, but I do need to check my 10% condition. That needs to happen. We're not going to do that yet. When we do the next example, we will. This is just meant to help us analyze what's going on. And by the way, this condition is met here. But when we're calculating the spread, the standard deviation of the sample means, it's your population standard deviation divided by the square root of your sample size. And so in this case, 550 divided by the square root of 1, I just get 550 grams. All right, so that's our center, and that's our spread. Now we're going to figure out shape. And in the prompt itself, did it tell us the shape? Did it tell us anything about the shape? And the answer is no. The shape was not stated as normal or as approximate normal. And our sample size is 1. So because it's not stated as normal, I'm thinking about case number 2. I have to have a large enough sample size to apply the central limit theorem. So in this case, I do not have a large enough sample size. So I cannot apply the central limit theorem. That's what we're practicing is. We're practicing reading prompts properly. Now, if I look at the next one, you may go, well, this is the same one because look, it says right here, a baby. So, again, Mr. Rainsberg, your sample size is 1. I think you made a mistake. I think it's the same exact prompt. And if you do that, you got to go, it's Mr. Rainsberg. He didn't make a mistake. The birth weights of babies at a certain hospital are known to be normally distributed. Look at that. They are known to be normally distributed. So you know what? it is stating my shape as being normal. The center, same idea. The mean of your sample means is an unbiased estimator of population mean, and so I'm going to get 3,250 grams. Standard deviation is going to be the population standard deviation over the square root of n, so 550 over the square root of 1, which is 550 grams. Alright, so does the central limit theorem apply? Now in this case, the central limit theorem does not apply, but I can still do the calculations as if it is normal. There is still approximately normal for your sampling distribution, because if the population is normal, if your population is normal, it doesn't matter how small the sample size. It doesn't matter how small the sample size. The sampling distribution of x bar is approximately normal. So, if the population is approximately normal, then the sampling distribution of x bar is normal. So even though the central limit theorem does not apply, you can still do calculations in this prompt dealing with normality. Alright, next one. In this case, we have a sample size of 5. But I'm still going to look at the entire prompt. It is known to be skewed right for the shape. So it is not stated as normal. It is stated as right skewed. And again, my mu of x bar equals mu, which is 3250 grams. My standard deviation of x bar is standard deviation over square root of n. It's just fun to write it down all the time. So 550 over the square root of 1, which is 550 grams. Alright, so I got my center, I got my spread, I got my shape as being skewed right, not normal. My sample size is 5, and in this case, the central limit theorem doesn't apply. Nope, it is not large enough. It is not large enough for us to do it, so therefore we cannot approximate. We cannot approximate normality with the sampling distribution. Of x bar. We cannot approximate normality. We cannot do normal calculations with this scenario. Next one. The birth rates of babies at a certain hospital are known to be skewed right. Look at that. So I'm going to do this. It is not normal. I'm going to circle that right away. It is not stated as normal. Alright, so here we go. I have all the information written down here. It's skewed right, so it's not normal. I have a sample of 30. I have my mean and standard deviation the same as it has been before. Alright, so can I apply the central limit theorem here? Well, my sample size is at least 30, so it does apply. I can perform normal calculations in this situation because the sampling distribution of x bar is approximately normal. It is approximately normal. So I would be able to use this with normal calculations because, oh no, the population is right skewed, but good enough because my sample size is greater than or equal to 30, so I am going to be able to do this. So now we're going to close this up with an example dealing with Instagram likes. Let's do the last problem here. This last problem deals with the gram. We're looking at Instagram likes. One important thing about this problem to pay attention to is that it uses the 4-step process: state, plan, do, conclude. This is the procedure that we use for inference for a lot of our free response problems. So make sure you're paying attention because in the future chapters, chapters 8 and beyond, when we do inference, we perform inference, we're going to set up our work using this 4-step process. So you're going to see this a lot in this chapter. So pay attention to how we do the state, the plan, the do, and the conclude. So this problem says, suppose the average number of likes on an Instagram photo is 26.2 with the standard deviation of 94.1. Assuming students at your school are typical of Instagram users, how likely is it that 30 randomly selected photos from students at your school will average at least 50 likes? All right, so before we do this, here's the state. And so what this problem, you have the original prompt, and what states is what you're going to be writing in the future. So what are you trying to find? Well, we want to know what is the probability that the average number of likes for 30 randomly selected photos is at least 50. So notice it includes what we're trying to find. It includes the sample size there. So by the way, let's define what's our population and what's our sample. And in this case, our population here is all photos posted on Instagram. All photos posted on Instagram. And the sample is the 30 that we found. So our sample here is the 30 random photos from students at our school. That is our population, and then we have our sample, the 30. And I define those. I state them. I'm going to say it again. If you don't define it, you don't get to use it. So I'm going to define my n, capital N, my population. I'm going to define my lowercase n, my sample. And one thing I do want to pay attention to here, and I don't want to kind of go past this, is I want to talk about, if I read this prompt, I'm going to look for, does it describe it being random? And so I want to find, hey, is it random? And so in this case, does it say random? And it says yes. You know, it says the prompt uses a random sample. The prompt does state randomly selected. So that's done. If I also go through and take a look at this, you know, do I describe a center? Is a center given to me? And it is. It says the mean is 26.2. Suppose the average number of likes. What you expect the average number of likes to be on an Instagram photo, 26.2. So it tells me my center. What about the spread? Well, in this case, it does tell you the spread. It says that it is 94.1 likes. So I have a spread here. But does it tell you the shape? Shape, center, spread. Is it random? And these are things you want to look for throughout here. And so when I'm reading the prompts and I'm going through it, yeah, I have the state, the plan to do, conclude I'm going to do, but I'm also going to make sure I'm looking for, was it done randomly? Because if it was done randomly and done properly, I can apply inference steps. What's the center? What's the spread? And does it tell me shape? And in this case, it does not describe shape. I don't know whether it's a normal population, approximately normal shape for the population, or if it's skewed right or if it's skewed left. I have no idea what the shape of the population is going to be. And so in this case, since I don't know my shape, since my shape is unknown, I'm going to be applying, most likely, my central limit theorem. So let's look at plan. So the sampling distribution of the sample means, x bar, for 30 photos has, and so here's where we're going to do all of our calculations. I know my mean, so mu of x bar, the average of the averages, the mean of the sample mean. So the mean of the sample mean is going to be equal to your population mean. And so in this case, it was 26.2. So there is my center. Shape, center, spread, center, done. Now, spread deals with our standard deviation. However, I do want to, and I'm going to find this first, is I want to make sure I have the right idea. I know I'm going to check my 10% condition. Is 10 times my sample size smaller than my population? So 10 times 30, is that less than or equal to my population? So is 300 less than or equal to n? And in this case, let's think about that. And I can do a better n than that. Are there more than 300 photos on Instagram? And yes, it is. And you have to make this statement. It is safe to assume that there is more than 300 photos on Instagram. So you don't just stop here and go, okay, you have to make the statement. You have to say, hey, you know what? It is safe to assume that there's more than 300 photos on Instagram. And because of that, since we did our 10% condition, I could say the standard deviation of my sample means is equal to my standard deviation divided by the square root of my sample size. You need to check that 10% condition. That's part of your spread, the idea of sampling without replacement on it. So make sure you do this. Make sure you're looking at that, and that's part of connected to the spread. So if I take a look at this, I'm going to say, what was it, 94.1 square root of 30. If I type that in my calculator, it's approximately 17.18. So I have my center, I have my spread, I need my shape. So if I take a look, the shape of the distribution was not stated. It was not stated. But since our sample size is greater than or equal to 30, so since n is greater than or equal to 30, we can use the central limit theorem. And by the way, CLT is for central limit theorem, and we can use that abbreviation. That is acceptable. The central limit theorem applies, and the shape of the sampling distribution is approximately normal. Not the shape of the population. We don't know that, but we can say the shape of the sampling distribution is approximately normal. So therefore, I know I have shape is approximately normal. I have center, and I have spread, which means I can do the problem. So let's do the do step. I want to find the probability of having an average of more than 50 likes. So I have my normal distribution, and I'm going to write it down again. Shape, center, spread. And I'm going to draw it out. Are we ready? Boom. There we go. Now, I want to figure out where I'm going to be at. So I want the probability of greater than or equal to 50 likes. So it's going to be somewhere around here, and I'm going to shade over to the right. So here is, and I'm going to write down 50. That's what I'm looking for. I have my shape, I have my center, I have my spread. Perfect. And so now I'm going to find my z. So I have my z-score, because it's approximately normal, which means, hey, table A. So I can do 50 minus what we observed minus what we expected over the standard deviation of the statistic. So boom. And that's going to give me a z-score of about 1.39. So I want the probability that z is greater than or equal to 1.39. And that's what we see over there in that shaded region. And I'm going to check it, by the way, is I like to do this because I can see I am at about, here's one standard deviation, here's two. I can see I'm in the right location. So that means my z-score is most likely right. Now, for me, I have my shape, I have my center, I have my spread, I have it shaded, I have it drawn. I like to go to the calculator. And I will show you down below, I'll do second distribution, normal CDF. And it goes lower bound. In this case, my lower bound is 50. So I have 50. My upper bound, well, I'm going to pick a really, really big number, so 9999999. My mean, we said, was 26.2. And my standard deviation was 17.18. So normal CDF, 50, comma 9999999, maybe it's one too many nines, 26.2, 17.18, hit enter, and I'm going to get 0.0829. So I have that, and I could say using calculator, and I'll write it down, normal CDF, I have 50, 99999, I have my mean, I have my standard deviation. You know what? I'm also going to do this. Here is my lower bound. Here is my upper bound. Here is my mean. And here is my standard deviation. Look at that. Shape, center, spread all across the board everywhere. I think I would get an E, maybe an E plus on this one. And so I have the probability of x bar being greater than or equal to 50 is approximately 0.83. 0.083. All right, so let's conclude. There is an 8.3% chance that 30 randomly selected Instagram photos will have at least 50 likes. Now, here's what I want you to realize about conclude. Notice it does say the sample size, because this is all based off of a sampling distribution where you had a sample of 30, a sample of 30, a sample of 30. So this distribution right here, that distribution is based solely on samples of size 30. So anything dealing in there is based off of samples of size 30. So you have to state that in the conclusion. And I'm also stating, what am I looking at? I'm looking at least 50 likes, because that's what we calculated there. So we have that. There's our state, our plan, our do, our conclude. Now, one thing to keep in mind, and we talked about this in the beginning, and I'll reiterate it now. This is a summary of Chapter 7. We are beginning the idea of inference. And so the idea is you have a population parameter, and you have to ask yourself, is it categorical or is it quantitative? So is it a proportion or is it a mean? And you can see the general idea for all of it. And notice what's very interesting is the idea that you have unbiased estimators for your center, that mu of x bar equals mu. Mu p hat equals p. That's not bad. You have the 10% condition for both of them. The one thing that is different is the shape. Now, if the population distribution is normal, you can have a small sample size, it's not a big deal. But for means, if the population is not normal or unknown, you need the central limit theorem. For proportions, for a sampling distribution of p hat, you have to have at least 10 successes. N times p has to be greater than or equal to 10, and 10 failures. N times 1 minus p greater than or equal to 10. So this is a really good slide that summarizes all the conditions in Chapter 7. So that is the end of lesson 7.3.